Hi, welcome back. Fourier Series Part 2, Complex Exponential Fourier Series. The Fourier series can be used to represent a periodic signal as a weighted sum of harmonically related cosine and sine waves. Basically, this is a function in time domain. We can represent this with a set of cosine and sine waves as shown in this figure here, where this is the original function. We can get the first harmonic, third harmonic, fifth harmonic. Basically, we get odd harmonic for this particular function. And then when you add the first harmonic, which is in the red color, and the third harmonic in green color, and what is in the orange color, the fifth harmonic, when you add these three harmonics, we get the one in blue color. Basically, it is a bit closer to the original signal than any of the other harmonics. So likewise, if we add more than 3, we can get a little bit closer to the original signal. For example, here, when you add 9 of the harmonics, we can get this kind of a signal. So this is the original signal was a square waveform, and now we get this kind of waveform. So basically, we can use sine and cosine functions to represent a given signal in time domain. So in general, we can write an expression for any periodic signal GPT. GPT is equal to A0, which is the average value, plus a series of cos functions and sine functions with an amplitude an and amplitude bn, and n goes from 1 to infinity. And this is 2 pi nt over t0. T0 is the periodic value of this signal. And actually, these cosine and sine terms also known as the basis functions. And T0 is normally known as fundamental frequency F0, and if you take 1 over T0, which is equal to F0. And in this case, what we are going to look at in complex exponential Fourier series is that instead of cosine and sine terms, the Fourier series may be represented in a compact form using complex exponential. Using the relations which we know quite often, we know that cos theta equal to half e to the j theta plus e to the minus j theta. In this case, theta is equal to 2 pi nt over t0, and 2 pi nt over t0, negative 2 pi nt, negative j 2 pi nt over t0. This is for cos. And similarly, sine theta equal to 1 over 2j e to the j theta minus e to the minus j theta. So we are going to use these representations to replace the original waveform, that the original function that we got for a periodic signal GPT, and instead of cos we are going to substitute the value here, and instead of sine we substitute this one. So basically we will end up with a function in terms of exponentials as opposed to the function with cos and sine. So that's why we call it an exponential Fourier series. So this is a long function here. Basically what we see here is that we have GPT A0 plus 2 times when you substitute for an, we substitute for cos in terms of exponential, and sine in terms of exponential. We get we can bring the terms together, positive exponential here and the negative exponential here, and then coefficient an minus jbn, an plus jbn. And now we are going to reorder these terms by basically we remove the brackets here. We get the summations, two summations, and one summation. If you notice here, it is an plus jbn exponential negative j2 pi nt over t0. So instead of this negative sign, what we do here, this term is as it is, but we are going to change this to a different term starting from negative infinity to negative 1. Basically what we do is we take the negative out, basically replace n with the negative n, and then we get this function. And this is please note that this is a modulus of n, and modulus of n is a suffix here. Anyway, so in general we can collect these terms and find out a function which goes from negative series which goes from negative infinity to positive infinity, negative infinity to negative 1, and this is actually when n equal to 0, and this n equal to 1 to infinity. So if you combine all these three, we can get n equal to negative infinity to positive infinity Cn, new coefficient, exponential j 2 pi nt over t0. So let's see what is Cn is. Actually, this is what we saw so far, and this Cn is actually an minus jbn when n is greater than 0. When n equals 0, that's the average value. Cn become a0, and otherwise an plus jbn. Okay, this is actually this is the complex exponential Fourier series. GPT can be represented by this kind of function, and Cn can be calculated by using the integral of k plus t0 GPT. GPT is a periodic signal that we are going to convert into a series of exponentials and integrate it with respect to t after multiplying exponential minus j 2 pi nt or t0. Please note that is a negative sign here, and 1 over t0 is the periodic time period. This t0 is periodic time of the signal. Okay, let's see an example here in which we are going to compute the complex Fourier coefficient Cn for the periodic pulse train GPT, summation of k minus infinity plus infinity p t minus k t0. Basically, it's a pulse train like this. This pt is one of these pulses, is known as this function here. Pt is equal to a whenever it is minus t by 2 to plus t by 2. In between minus t by 2 plus t by 2, pt has a value a, otherwise its value is 0. And it has a periodicity t0 because from here, center of this gap to the center of this gap, the distance is t0. And actually capital T should be less than t0, otherwise you get a we won't get this the space in between, and it will become a continuous DC signal. Okay, now we are going to apply the function, the complex Fourier coefficient that we got just now, that is Cn equal to 1 over t0 minus t0 by 2 to plus t0 by 2 GPT exponential minus j 2 pi nt over capital T0. Note this negative sign, and GPT is the function in time domain, and the periodicity is t0. It's t0, 1 over t0. It goes from minus t0 by 2 to plus t0 by 2. If you look at it again, minus t0 by 2 to plus t0 by 2. This is one periodic time of the pulse here. And also we note that the pulse only exists between minus t by 2 to plus t by 2. That is, during that time the amplitude is a. Otherwise amplitude was 0. Amplitude is 0. So what we can see in the next step here is that 1 over t0, instead of minus t0 by 2, we substitute t by 2, minus t by 2 to plus t by 2, and GPT will become capital A because that is the amplitude of the signal during minus t by 2 to plus t by 2, A. Before minus t by 2 it was 0, after t by 2 it is 0 until t0. So basically the function exists only between minus t by 2 to plus t by 2, not minus t0 by 2, t0 by 2. T0 is the periodic time, but the function does not exist for certain time period. And then multiply by a exponential minus j 2 pi nt over t0 dt. So when you integrate this one, we can see this function here. Basically, after integrating, when you integrate exponential function, you get exponential alpha t. So it basically exponential alpha t divided by alpha. So after ordering some terms, you can end up with this function here. Basically, it's a sinc function. This one is actually 1 over n pi sine 2 n pi t over capital T0, and because of n pi in down here, we can write it in this form: sine pi nt over t0, pi nt over t0, and we put a similar term down here to bring it like a sinc function, and then we multiply by this term to get rid of the terms that you have put extra, the values, the extra values here. So then after ordering the terms, we can get a function called sinc function. Basically, sinc function is defined by sine pi x over pi x. So if you have a term like this one divided by this one, we can write sinc x. Please note the pi is not here. Sine pi x over pi x equal to sinc x. So if you have sine pi nt over t0 divided by pi nt over t0 will become sinc nt over t0. Pi will not be here, and the amplitude is ta over t0. The function actually looks like this, so which has an amplitude equal to 1 here, sinc function, and in this particular case this is 1, and multiply by ta over t0 as the amplitude here. So this is the sinc function that you get here. Basically, the coefficient Cn is a sinc function. Now let's see how the sinc function behaves because we have discontinued values, because n is not a continuous function here. N is basically n is an integer, and the amplitude spectrum of GPT can be written, actually Cn is the amplitude spectrum that we got just now, but if we plot that, you can see that basically it has values only when n has a value. Basically, for discrete values of uh, sinc function, or when you put a value for n equal to 0, you get 1, and the amplitude is t over t0, n equal to 2, you get a value for sinc 3, like that. We can see the amplitude. Basically, this is the modulus of Cn without any negative sign. So check the modulus, so always positive. Earlier we observed that sinc function goes to negative, but in this case we took the modulus, therefore it's positive here. So then each value of n will give us an impulse here. So the separation between two impulses here is equal to 1 over t0. That is the fundamental frequency of this particular periodic signal. And also we can see that there is a phase. In this case, phase is when it is positive, phase is we take phase to be 0, and when it is negative, it depends on whether it's approaching from negative side or positive side. Basically, we sometimes divide it, take it as an odd function, because sinc is the odd function in this case. So basically we take the positive sign. In this case, the angle goes from 0 to negative 180 and 0 to positive 180. Basically, the angle is out of phase to the previous one. This will be 0 phase, this will be 180 phase, negative 180 phase. 0 is positive and negative 180. So basically, sinc function goes to negative. There's a solution to this particular problem, and you need to make sure that the function is not continuous in a frequency domain. This is actually amplitude spectrum in one. This is actually, we can say it's in frequency domain, where it is in terms of 1 over t0 is frequency. So there is a discontinued pulses in this domain. Thank you.